Alrighty, I'm back. Um, yeah, over the break, I watched a couple of videos on computing history, and one of them was actually a Feynman thing. It's all AI generated stuff on YouTube, which might normally put me off of it, but it was really good. It was a synopsis of what the Feynman technique of learning, and obviously it's something I ran into. I grew up on Feynman. I've read his books. I watched all of his lectures. I watched his private interviews. I've kind of spent a lot of my early life learning about Feynman, but I never really grokked the Feynman technique. And this video was on the Feynman technique, which is not to sit down and do kind of what I've been doing for the past couple months, which is just laboriously reading and studying. And it's more to be laser focused in finding the things that you need to consume to understand something, to build up that understanding. And it's something that he also did is he had a map of his ignorance. And I feel like I need to start that now. I'm putting in a learn log. I want it to be Excalibur drawing. Did I fuck this thing up? Yeah, I probably did. There we go. Let's see here. Can I just do reset? Yeah. Okay, there we go. I wonder if this is something I should invest the time into doing right now. It's kind of a side quest. I want to do it, but I feel like it could just be something that I do. It occupies a bunch of time, and doing it, I don't get value out of it. I think maybe better would be instead of a graphical map, have a textual one, because I'm not feeling a visual representation here. So ignorance map. What blogs aren't really okay. stays. There used to be a website for this. Okay. That was, I think, it's a bit of a side tangent. Fleshing out the ignorance list, reorganizing things into production and consumption tracks. Um, yeah, it's a bit of a side quest there. But I feel like it's something I needed to do. All right, let's launch our calendar. I also got a notification that my APOD meeting will be earlier tomorrow. So we've been going for about an hour, a little over an hour, working on that. I didn't plan on doing that, but I mean, this time is not strictly necessarily focused on content, consuming content here. Last night I did the perspective stream, and I got a lot out of it, and I feel like I did a little bit of that here this afternoon. One thing I noticed is this morning I woke up, I had a lot of energy. I was really well rested. So I'm wondering if I could get more stuff done in the evening. If I, instead of doing wind down time, if I say, hey, I'm not going to fuck around, wind down, how about we just do more reading? Or, we could pick any topic of choice. How about that? We don't have to read the stuff that we're laser focused on right now. We could have wind down time be more like have fun time, because that's basically what it is on Wednesday. I got like D&D until 8 anyways, so now if I get to bed at 8, wake up at 4:30 is pretty reasonable. Yeah. Let's try it again. Let's try it again tonight. I'm not going to force it. We'll call this a evening fun stream. Do whatever I want stream. It's supposed to be something reasonably productive. It doesn't have to be insanely productive. It could be even like consuming like video stuff. But something like reasonably productive instead of wind down time. Like sometimes when I get off the stream, my wind down is like, let's get on YouTube, let's watch politics, let's watch markets, let's do or let's watch sci-fi or something entertaining, or the worst of the worst, YouTube shorts. Like all those things, I feel like they don't really wind me down, but they're things that I'm tempted into when I'm not on stream doing things. So I'd rather just say like 6 to 8 is my time where I just do whatever I want. I could pick up a book that I haven't even touched just to like read a summary of a chapter, or I could watch a conference talk. I could do whatever the hell I want, but it's something related to personal improvement, either like fitness or learning about computation or mathematics, or something focused on making my life better instead of what I use it for now, which is to just fuck off and like waste time playing video games, watching YouTube, just like wasting my life. So while I do respect that I need some time to kind of just like wind down without screens, last night I was able to get to bed pretty shortly after I got off stream, and I woke up feeling amazing. So if I can do that last night, let's try it again tonight and see if it works. Anyways, that's where I was thinking maybe tonight I get a couple more hours in. let's get back to the reading. We finished this problem. I'm pretty sure we got up to 5.7. Yeah. Understanding modern processes. Up to this point, we have applied optimizations that did not rely on any features of a target machine. They simply reduced the overhead of procedure calls and eliminated some of the critical optimization blockers that cause difficulties for optimizing compilers. As we seek to push the performance further, we must consider optimizations that exploit the microarchitecture of the processor, that is, the underlying system by which the processor executes instructions. The microarchitecture. So this is beyond the ISA. It's actually understanding how the ISA is implemented. Getting every last bit of performance requires a detailed analysis of the program as well as code generation tuned for the target processor. Nonetheless, we can apply some basic optimizations that will yield an overall performance improvement on a large class of processors. The detailed performance results we report here may not hold for other machines, but the general principles of operation and optimization apply to a wide variety of machines. To understand ways to improve performance, we require a basic understanding of the microarchitecture of modern processors. Due to the large number of transistors that can't be integrated onto a single chip, modern microprocessors employ complex hardware that attempts to maximize program performance. One result is that their actual operation is far different from the view that is perceived by looking at machine-level programs. At the code level, it appears as if the instructions are executed one at a time, where each instruction involves fetching values from registers or memory, performing an operation, and storing results back to a register or memory location. In the actual processor, a number of instructions are evaluated simultaneously, a phenomenon referred to as instruction level parallelism. So it's like pipelining, prefetching, and stuff like that. In some designs, there can be 100 or more instructions in flight. Elaborate mechanisms are employed to make sure the behavior of this parallel execution exactly captures the sequential semantic model required by the machine-level program. This is one of the remarkable feats of modern microprocessors. They employ complex and exotic microarchitectures in which multiple instructions can be executed in parallel, while presenting an operational view of simple sequential instruction execution. Although the detailed design of a modern microprocessor is well beyond the scope of this book, having a general idea of the principles by which they operate suffice to understand how they achieve instruction level parallelism. We will find that two different lower bounds characterize the maximum performance of a program. The latency bound is encountered when a series of operations must be performed in strict sequence. Because the result of one operation is required for the next before the next one can begin. This bound can limit program performance when the data dependencies in the code limit the ability of the processor to exploit instruction level parallelism. The throughput bound characterizes the raw computing capacity of the processor's functional units. This bound becomes the ultimate limit on program performance. So this would be how many lanes you have in your pipeline. So this is all cool stuff. I'm glad we're getting into it. I do want to kind of like check something really quick before we continue reading, which is my README. So we got up to 5.7. Yeah. So let me check the index here. So up to 5.7, but not including 5.7. So that's basically it's like about 20 or say 16 pages. And then to the end of this would be 604. So we got a lot more to go. Got about 50 pages left to go. So probably not going to finish this chapter today. That's fine. Overall operation. Figure 1511, which is on the next page here. Figure 511 shows a very simplified view of a modern microprocessor. Our hypothetical processor design is based loosely on the structure of a recent Intel processor. These processors are described in the industry as being superscalar, which means that they can perform multiple operations on every clock cycle, and out of order, which means that they can perform, meaning that the order in which the instructions execute need not correspond to the ordering of the machine level program. So scalar would be one operation per clock cycle. Superscalar is multiple, which is kind of related to instruction level parallelism. You achieve superscalar operation by instruction level parallelism. The overall design has two main parts: the instruction control unit, which is responsible for reading a sequence of instructions from memory and generating from these a set of primitive operations to perform on program data. And the execution unit, which then executes these operations. Compared to a simple in-order pipeline we studied in chapter 4, I didn't read that, out-of-order processes require far greater and more complex hardware, but they are better at achieving higher degrees of instruction level parallelism. The ICU reads the instructions from an instruction cache, a special high-speed memory containing the most recently accessed instructions. In general, the ICU fetches well ahead of the current executing instructions so that it has enough time to decode these and send operations down to the execution unit. One problem, however, is that when a program hits a branch, we use the term branch specifically to refer to conditional jump instructions, other instructions that can transfer control to multiple destinations such as procedure return and indirect jumps, provide similar challenges for the processor. One problem is, however, when a program hits a branch, there are two possible directions the program might go. The branch may be taken with control passing to the branch target. Alternatively, the branch can be not taken with control passing to the next instruction in the instruction sequence. Modern processors employ a technique known as branch prediction, in which they guess whether or not a branch will be taken and also predict the target address for the branch. Using a technique known as speculative execution, the processor begins fetching and decoding instructions at where it predicts the branch will go. It even begins executing those operations before it has been determined whether or not the branch prediction was correct. If it later determines that the branch prediction was incorrect, it resets the state to that at the branch point and begins fetching and executing instructions in the other direction. The block labeled fetch control incorporates branch prediction to perform the task of determining which instruction to fetch. So we got our instruction control unit. It's got quite a lot of stuff in here. It's got an instruction cache, Those go to an instruction decode, which go to operations to the execution unit. There's also fetch control. There's a retirement unit and a register file. These operations go to arithmetic, load and store from memory and cache, and branching, which then talks to fetch control. Okay. The instruction decoding logic takes the actual program instruction and converts them into a set of primitive operations, sometimes referred to as micro-operations. Each of these operations performs some simple computational task, such as adding two numbers, reading data from memory, or writing data to memory. Machines with complex instructions, such as x86-64 processor, an instruction can be decoded into multiple operations. The details of how instructions are decoded into sequences of operations varies between machines, and this information is considered highly proprietary. Fortunately, we can optimize our programs without knowing the low-level details of a particular machine implementation. In a typical x86 implementation, an instruction that only operates on registers, such as add Q REX to RDX, is converted into a single operation. On the other hand, an instruction invoking one or more memory references, such as add Q REX 8 offset from RDX, yields multiple operations, separating the memory references from the arithmetic operations. This particular instruction would be decoded as 3 operations: one to load a value from memory into a processor, one to add the loaded value to the value in the register EAX, and one to store the result back to memory. The decoding splits instructions to allow a division of labor among a set of dedicated hardware units. These units can then execute the different parts of multiple instructions in parallel. The EU receives, execution unit, not European Union, receives operations from the instruction fetch unit. Typically, it can receive a number of them on each clock cycle. These operations are dispatched to set a set of functional units that perform the actual operations. These functional units are specialized to handle different types of operations. Reading and writing memory is implemented by the load and store units. The load unit handles operations that read data from the memory into the processor. This unit has an adder to perform address computations. Similarly, the store unit handles operations that write data from the processor into the memory. It also has an adder to perform address computations. As shown in the figure, the load and store units access memory via data cache, high-speed memory containing the most recently accessed data values. With speculative execution, the operations are evaluated, but the final results are not stored in the program registers or data memory until the processor can be certain that these instructions should actually have been executed. Branch operations are sent to the execution unit not to determine where the branch should go, but rather to determine whether or not they were predicted correctly. If the prediction was incorrect, the execution unit will discard the results and that have been computed beyond the branch point. It will also signal the branch unit that the prediction was incorrect and indicate the correct branch destination. In this case, the branch unit begins fetching at the new location, as we saw in section 366. Such a misprediction incurs a significant cost in performance. It takes a while before a new instruction can be fetched, decoded, and sent to the functional units. Figure 511. Where's 511? It's back over here. We just looked at. Indicates that different functional units are designed to perform different operations. Those labeled performing arithmetic operations are typically specialized to perform different combinations of integer and floating point operations. As the number of transistors that can be integrated into a single microprocessor chip has grown over time, successive models of microprocessors have increased the total number of functional units. The combinations of operations each unit can perform and the performance of each of these units, the arithmetic units are intentionally designed to be able to perform a variety of different operations, since the required operations vary widely across different programs. For example, some programs might involve many integer operations, while others may require floating point operations. If one functional unit were specialized to perform integer operations, while another could only perform floating point operations, then none of these programs would get the full benefit of having multiple functional units. For example, our Intel Core i7 Haswell reference machine has 8 functional units, numbered 0 through 7. Here's a partial list of one's capabilities: integer arithmetic, floating point multiplication, integer and floating point division branches, integer arithmetic, floating point addition, integer multiplication, floating point multiplication, load, address computation, load, same thing, store, integer arithmetic branches, store, address computation. And the above list, integer arithmetic refers to basic operations such as addition, bitwise operations, and shifting. Multiplication and division require more specialized resources. We see a store operation requires 2 functional units, one to compute the store address and one to actually store the data. We will discuss the mechanism of store and load operation in section 512. We can see that this combination of functional units has the potential to perform multiple operations of the same type simultaneously. It has 4 units capable of performing integer operations, 2 that can perform load operations, and 2 that can perform floating point multiplication. We will later see the impact of these resources have on the maximum performance our programs can achieve. Within the ICU, the retirement unit keeps track of the ongoing processing and makes sure that it obeys the sequential semantics of the machine level program. Our figure shows a register file containing the integer, floating point, and more recently SSE and AVX registers as part of the retirement unit, because this unit controls the updating of these registers. As an instruction is decoded, information about it is first placed into a first in, first out queue. This information remains in the queue until one of 2 outcomes occurs. First, once the operation for the instructions have completed and any branch points leading to the instruction are confirmed as having been correctly predicted, the instruction can be retired, with any updates to the program registers being made. If some branch point leading to this instruction was mispredicted, on the other hand, the instruction will be flushed, discarding any results that may have been computed. By this means, misprediction will not alter the program state. As we have described, any updates to the program register occur only as instructions are being retired on. Let's read this aside. History of out-of-order processing. Out-of-order processing was first implemented in the Control Data Corporation 6600 processor in 1964. Jesus, that's a long time ago. Instructions were processed by 10 different functional units, each of which could be operated independently. In its day, this machine, with a clock rate of 10 megahertz, was considered the premium machine for scientific computing. IBM first implemented out-of-order processing with the IBM 36091 processor in 1966, but just to execute the floating point instructions. For around 25 years, out-of-order processing was considered an exotic technology found only in machines striving for the highest possible performance, until IBM reintroduced it in the RS-6000 line of workstations in 1990. This design became the basis for the IBM Motorola PowerPC line, with the model 601 introduced in 1993 becoming the first single-chip microprocessor to use out-of-order processing. Intel introduced out-of-order processing with its Pentium Pro model in 1995, with an underlying microarchitecture similar to that of our reference machine. As we have described, any updates to the program register only occur as instructions are being retired, and this takes place only after the processor can be certain that any branches leading to this instruction have been correctly predicted. To expedite the communication of results from one instruction to another, much of this information is exchanged among the execution units, shown in the figure as operational results. I didn't see that. As the arrow in the figure show, the execution units can send results directly to each other. This is more elaborate form of data forwarding techniques we incorporated into our simple processor design in section 455. The most common mechanism for controlling the communication of operands among the execution unit is called register renaming. When an instruction that updates register R is decoded, a tag T is generated giving a unique identifier to the results of the operation. An entry RT is added to a table maintaining the association between program register R and tag T for an operation that will update this register. When a subsequent instruction uses register R as an operand is decoded, the operation sent to the execution unit will contain T as the source for the operand value. When some execution unit completes the first operation, it generates a result VT, indicating that the operation with tag T produced value V. Any operation waiting for T as a source will then use V as a source value and a form of data forwarding. Okay. By this mechanism, values can be forwarded directly from one operation to another rather than being written to and read from the register file, enabling the second operation to begin as soon as the first has completed. The renaming table only contains entries for registers having pending write operations. When a decoded instruction requires a register R and there is no tag associated with this register, the operand is retrieved directly from the register file. With the register renaming, an entire sequence of operations can be performed speculatively, even though the registers are updated only after the processor is certain of the branch outcomes. So these are some latencies of different operations. So we got operation, addition, multiplication, division between integer and floating point. We have our latencies, so division is really slow on everything. Float is a little bit slower than integer for addition and multiplication, and even division. Well, no, division, it's equal or faster. Issue, I don't know what issue means. Capacity, don't know what that means. Latency, issue time, it says issue time, and capacity characteristics of reference machine operations. Latency indicates total number of clock cycles required to perform the actual operation, while issue time indicates a minimum number of cycles between two independent operations. The capacity indicates how many of these operations can be issued simultaneously. The times for division depend on the data values. All right, functional unit performance. This stuff's getting a little dry. So you got function unit, an abstract model of processor operation. And they get from machine code to data flow graphs. Other performance factors. And then we got a couple of problems, and we get into loop unrolling after this. This shit is dry as fuck. Let's watch the lecture then, because he had a really good lecture, to be honest, on performance. Oops. I don't mind rewatching it. I didn't quite grok it when you first give it.
We've now gotten through all the lectures on machine code, and we're starting to talk about, okay, now that you know this stuff, what can you do with it? And this lecture is along the lines of that. This is sort of what you are now empowered to do now that you can look at and understand machine code. This material is a little, this actually there's a whole chapter of the book, chapter 5, on performance optimization, and we're only going to do one lecture on it. And we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic and one I think you'd find yourself well equipped for. There are typically a few chapters now empowered to do now that you can look at and understand machine code. This material is a little, there's a whole chapter of the book, chapter 5, on performance optimization, and we're only going to do one lecture on it. And we don't have any labs, unfortunately, that really get you to push your limits on this, which is too bad because it's a very interesting topic and one I think you'd find yourself well equipped for. There are typically a few small exam problems that are sort of based on some of the material here you'll find in old exams. But really the idea is, how can I make programs run fast? Given that I've sort of know what algorithm I'm using and I've perhaps gotten a program that runs, how can I make it run faster? And one of the themes of it is you can sort of do this in layers. You can sort of, first of all, do the stuff to avoid sort of things that make programs run slow across a wide variety of machines. And just make I would describe it as making your code more compiler friendly, and we'll talk about what that means. And you have to have some understanding and appreciation for what compilers are good at and what they're not good at to be able to do that. And I describe these as the kind of things that you should just be in the habit of when you write programs, writing this code that I'll describe as compiler friendly. And then the next level is, okay, given that I've sort of taken away the things that really shouldn't have been there in the first place, now how can I make my programs run faster? In particular, how can I adapt it to the capabilities of the types of machines that this program is going to run on? And that can, again, go from ones that will generally make programs run fast across a wide variety of machines to ones that become very specific. And very specific is a risky thing because even in the world of, say, x86 machines, there's quite a variety of them that are available at any given point in time, and they evolve over time as well. So you can make a program run really fast on one particular model of one x86 processor, but it might not, that if you're trying too hard, you'll find your effort is sort of wasted when you move it to another. On the other hand, these general ideas I'm going to describe actually work across quite a range of machines. So, and I'll talk about that more as we go along. So, it used to be in the bad old days that if you wanted a program to run fast, you had to write it in assembly code. And that's just plain not true anymore. And if anyone tells you it's true, it's because they're full of it. It's just not true. Except for the exceptional case where you're running on a very small resource-constrained machine, such as a very small underpowered embedded system. So let's just assume that we're going to use a compiler, and we'll assume for this course we're going to use GCC because it's generally available. It's not actually the best compiler out there. Intel makes a compiler that costs money to license and stuff, but it really can do some amazing things. And other compilers exist, but GCC is sort of a good enough compiler for most people. But there's some features of some things that sort of puzzle compilers that they don't really understand. Compilers don't really understand, for example, that the numbers you're using when you say it's an int might actually range over a much smaller set of values. And they have a very hard time understanding memory referencing patterns and the effect of procedure calls. And so in general, what happens with a compiler is it has a whole sort of cookbook of optimization strategies and some recipes for how to try out different strategies and apply them. But in general, if it ever feels like this code is something that it doesn't feel confident about being able to make certain transformations, then it just won't. It will keep things sort of a more direct implementation of exactly what you describe. And we'll show examples of that as we go along. So the thing about optimizing compilers, it always has a fallback position, which is to not optimize. And sometimes that will get in trouble if you want your program to run faster and the compiler just, in its own conservative way, decides not to do that optimization. And one of the tricks that you'll find is pretty useful now that you can read assembly code is you run the compiler, you see what optimizations it does, and if it doesn't make something that you expect it to be able to do, you go back and figure it out. So it's very common, by the way, to rewrite your program in the same language and sort of tune it and up to make it run faster, to make it more compiler friendly. There's nothing wrong with that, as long as you don't then just totally obliterate the program and make it totally illegible. So let's just describe some sort of general optimizations. And you've actually seen versions of this in some of the assembly code we've already looked at. And I'll use mostly sort of examples from multi-dimensional arrays, because those are actually fairly easy optimization type of tasks. But these apply to other types of program as well. So you saw before when we described how to do array indexing in multi-dimensional arrays that the old style of code was if you had a variable size array, it was up to you, the programmer, to write the formula of how you convert row I, column J into a position in a one-dimensional array. So remember, it's just the number of columns times the row number plus the column number is the standard one. So that would give, this would be pretty typical code then. It would give you a notation like this. If you wanted to set one row in array A to the values in a one-dimensional row B, this is the code you'd write. And the main observation is within this loop, the only variable that's changing is J. And so from the array perspective, this computation n times I, if it gets repeated over and over again within this loop, then you're just wasting, it's a wasted effort. So you can do what's called code motion, which is to pre-compute the value of n times I outside of the loop, and then use it over and over again inside. And compilers will generally do this when they can detect, for example, that it's a array access code and it has this technique. It will generally do optimizations like this if you set, say, an optimization level of 1 or higher to.
I'm curious. Is the stack memory typically in the cache? Stack has a few properties that make it frequently cached. Spatial locality, stack frames are contiguous. Temporal localities, functions repeatedly access the same locals. Small working set, many functions use a small amount of stack. In practice, active portions of the stack are very often sitting in null and cache.
And we can see this, in fact, this is this code, and I ran it through GCC using optimization 1. And you see, as this red instruction shows, it boosted this multiplication outside of the loop. It's a little as if you actually, this code does even more. It turns the code into something that looks more like a pointer code, accessing array A and stepping through that element by element of the array. Another one, and we've seen this already, that when GCC turns a multiplication or a division by shifting and adding and operations like that, multiplication or division by constants. We've seen examples of that. And a similar one would happen if we took that program I showed before and applied it to every row. So we wanted to set for array A, we wanted to set every one of its rows to the value of the one-dimensional array B. Then again, if we took that code, we boosted the n times I in there. So now the inner loop is good, but you realize that this multiplication isn't necessary either, because what we're doing from I equals 0 to I equals 1 to I equals 2 is we're just increasing the parameter ni by, we're adding n to it. So we can, and that's called a reduction in strength. We've taken a multiplication and turned it into addition because there's some predictable pattern of how this variable ni is going to be updated. Another example, and again, array indexing is a good example for optimizations. Imagine we had an image that we represent as a two-dimensional array of pixel values. And we want to do something that's a filtering operation where we want to take the sum of the 4 neighbors of a given pixel, north, south, east, and west, and average those together, or sum them together. And so the natural way you'd write this in C is to say I want usually in images you count from the top down, and so you'd say this is the pixel above, this is the pixel below, this is the pixel to the left, and this is the pixel to the right. And if you do this and just compile it straight through, unfortunately, it appears as if there's 3 different multiplications by n, I minus 1, I plus 1, and I. And if the compiler isn't too clever, it won't realize that these are related to each other, and it will issue 3 different multiply operations just to do this one pixel thing. Whereas if I'm a little more clever, and this is one where I manually rewrote the code so that the compiler would pick it up, I'd say, well, if so ij is I times n plus j, and I can get the pixel above, the pixel below by shifting that, offsetting that by a value of n. And then it will issue the code. This will compile with the code with just one multiply. And in general, by the way, multiply used to be a very expensive instruction. Nowadays, there's enough hardware resources that it takes about 3 clock cycles, so it's not a huge deal. But anytime you can take 3 multiplies and use just one instead, that's generally a good idea. Question?
Isn't this optimizing for runtime, though? What if you're trying to optimize for space instead?
So the question is, what if you're trying to optimize for space? And there are a lot of optimizations that will make your code be bigger at the expense of, in order to go faster, right? This one, though, I'd argue this is actually shorter code, right? I mean, just look at the number of instructions. So, and usually, so code, that used to be a bigger concern when memory was sort of, back the original IBM PC had 640 kilobytes of memory, so in its maximum configuration, and that was a big deal to actually buy it that much. So, back then that was a big deal, memory. But nowadays, memory, the size of the program is usually a pretty small fraction of what you're dealing with overall. But it's a valid question. OK, so that just shows you an example. And in general, compilers are pretty good at doing those low-level optimizations like that if you write the code in a way that's reasonable. But there's some other ones that the compiler, and even the fanciest compiler you can buy, might not be able to figure it out. And so I like to illustrate this with when the first term we ever taught 213, I was looking at some lab code that some of the students wrote, and I was horrified about this code. And I showed it to the TAs, and none of them figured out what was wrong. And I've shown it to many other highly trained C programmers, professionals. And they go, looks okay to me. So let's figure out why I was horrified by this code. So the idea of this code is supposed to be pretty straightforward. There's a string S, and I want to convert that string, all the characters in it, to lowercase. So I'm just going to read through the string, and for each string position, test that character. And if it's somewhere between uppercase A and uppercase Z, then I'm going to shift it to being between lowercase a and lowercase z. Otherwise, I won't change it. So pretty straightforward. But if you run this, you see that if you go up to 500,000 characters, which might sound like a lot, but it takes 240 or so 4 minutes to run this code. And you go, well, that's a pretty big string. It's really not a big string. You should be able to do lowercase conversion of a string in a lot less than 4 seconds. And you also notice this growth is nonlinear. It's quadratic. It's growing as the square of the string length. So this is not good. And unfortunately, it's the kind, and by the way, this is one of it's very easy, surprisingly easy to have programs that have some hidden performance bug that makes them run quadratic. And you run tests, and you test for strings of 10,000 or less, and it doesn't look like a big deal because the runtime is insignificant. So, but then all of a sudden it hits a really bad case. So this is there's something wrong here. So what's so bad about this program? Well, the key is when in a test like this of calling strlen, so the way it's determining whether it's reached the end of the string is by calling strlen to figure out how long the string is. And and remember, if we do the conversion of a for loop into a go-to form like you've seen, there's various ways to convert it, but all of them, the test gets built into the loop. So the main feature of that is this call to strlen will happen every time you go through the loop. And people overlook that fact. When you look at the different parts of a for loop, the initialization only gets executed once, but both the test and the update get incremented, get applied every time you run through the loop. So that's getting called as many times as there are characters in the loop, in the string, right? And now, how does strlen work? Remember, in C, the only way you know how long a string is to step through the whole thing and find the null character at the end. So strlen itself is a linear time operation in the string. And you're doing that, and so you're doing n calls to a function that takes time n. The string is getting shorter as you go, but not very fast. So basically, that's quadratic performance. And that explains why you get that runtime. So in particular, if I just make the following little change, I introduce a local variable called Glen, and I pre-compute strlen because the length of the string isn't changing. I'm just changing the characters in the string. So the program will do the same thing, but now the runtime is so short it doesn't even show up. It's maybe a second to do 1 million characters. It's just not a big deal at all, as it should be. It's just running through. And so that's just an example of one of many that I've seen in my career where something that seems almost insignificant turns out to be a serious performance problem. So why couldn't a compiler figure this out? why couldn't a smart compiler look at the original code and say, this is what the programmer wrote, but I know a better way to do it. I'll pre-compute Stirland in advance. Well, there's a couple of reasons. One is, actually, if you look at the code for Stirland, you see that it's actually modifying the string, and Stirland, the code here is modifying the string, and we're calling Stirland on it. So you'd have to be pretty careful to do the analysis, the compiler would, to figure out that even though the string is changing, the result you're going to get from Stirland is not going to change. Right? So that's one reason. And the second is, well, and how can the compiler be sure which version of Stirland is actually going to get used? You remember in C, each of the files gets compiled separately, and only afterwards does it all get brought together in the linking phase, and some of that even happens after the program gets started. So even though there's a standard Stirland function, it's not necessarily the case that that's the one that will actually get used in the final program. So the compiler really can't be sure of that. In particular, imagine I provided a sort of customized Stirland function like this that is keeping track of the sum of the lengths of all the strings that it's been called on, or some other side effect like that, that that program would produce a very different result than if whether or not I make the optimization. So the compiler has to assume that Stirland is just a black box that does whatever it does, and can't make any assumptions about what side effects it might have and so forth. So it won't make that optimization on any machine, even with the best compiler. So that's just an example that, you can tell that I've gotten kind of sensitized to this so that I spot these, but a lot of people don't. So let's look at this. Let's see. What am I looking at now? Oh, this is another bad example, a bad coding example. Imagine I want to compute for a two-dimensional array A and a one-dimensional array B. I want to make B sub I be the sum of all the elements in row I of A. So again, this is a fairly obvious kind of way to write this program, that you say, well, bi equals 0, and I'm going to just accumulate it. I'll step through the row and accumulate all the values. And of course, we know now we could improve this by moving I times n out and so forth. I'm not trying to illustrate that. But what you'll see in the program, this is in the inner loop. And we've looked briefly at some floating point instructions. And remember, the main feature of them is the move instructions look like the move ones you're familiar with, except when we put floating point data in one of these XMM registers. So the main thing you see here is it's reading from memory, it's adding something to it, and then it's writing back to memory. And what that memory location corresponds to B of I. So what it means is every time through this loop, it's having to do a memory read and a memory write of B, in addition to the memory read of A. Even though presumably B of I is the same value that you just updated it to in the previous execution of this loop, right? So why do you read it, why do you write it out and then read it back in, increment it, and then again copy it back out? Why does it have to keep jumping back and forth between memory and registers over and over again? Well, the reason is because in C you can't be sure that there isn't what's known as aliasing, and I'm demonstrating it here. Imagine if row B is just declared to be okay. So imagine, and you can do this in C. This is legal C code. You can make one memory data structure overlay another data structure. That's referred to as aliasing, when two sort of separate parts of the program are referring to the same locations in memory. And the C compiler has no way of knowing whether there's a lot of work in optimizing compilers to detect aliasing possibilities. But in general, it has to assume aliasing might happen. So imagine this aliasing happens so that array B corresponds then to this row of array A. Then, of course, its initial value is 4816. But if you trace through what this code will do, it has this sort of odd behavior that is probably not useful for anything. But it just demonstrates that what will happen is as as B gets updated, it's effectively changing A, and it's changing then what's being read during the summation. And so this is a real possibility in C. And so the compiler, when it's given code like this, it has to assume that these two memory locations might overlap each other. So that's why it's carefully writing it out and then reading it back in over and over again. And so if I just rewrite this code by introducing, again, a local variable and accumulating in that local variable, and then only at the end do I assign that to B sub I, then you'll see this exact same loop all of a sudden gets a lot simpler. It's just a read, floating point, read, and add to do that. And we'll see, in fact, the memory is actually one of the limiting performance limiters in a program. So this will be significantly faster. And again, that's something that you as a programmer would hardly think is a big deal. But the C compiler can't do that in general because it can't determine in advance what possible aliasing there can be. So as these two examples say, sort of get in the habit of introducing local variables and using them. And it's your way of telling the compiler, don't call the same function over and over again. Don't read and write the same memory location over and over again. Just hold it in a temporary one. And then it will automatically allocate a register and store it in that register, and everything will be good. OK, so that's sort of the kind of what we call optimization blockers, the kind of things that you as a programmer can make a difference on. And the main blockers are memory referencing, aliasing, and function calls, and sort of understanding what might happen in that function call. So now what we're going to do is transition. Question?
Yeah, two quick questions. So on the memory aliasing slide, there's this declaration of double B of array of size 3 equals A plus 3. This doesn't quite seem to be valid C code because I think C still makes a distinction between array and pointer.
No, this is valid C code. I'm sure this is valid C code because it ran. So this is initializing, calling it an array B. Remember, these are int stars. These aren't two-dimensional arrays, right?
Yeah.
So this is saying A is now think of it as a linear array of 4 elements, of 9 elements. And A plus 3 is just to go in 3. So it is declaring B is not a pointer, it's an array. But remember, with an array, you can use the name of that array as a reference to a pointer, a readable reference, not a writable reference, right?
But I'm currently using the GCC version 4.9 and just as invalid initializer.
Really? For this exact code?
Yeah.
Well, I'll double check it.
Oh, and also like a few slides before on the C style strings, is there a reason that this design of the C programming language use null-terminated strings instead of like Pascal-sized strings?
So the question is, why does C use null-terminated strings? And it does, and it might be a bad decision for multiple reasons, right? But I think in general, think of C was somebody who had, or a couple of people who had been writing a lot of assembly code and wanted to lift up that level so they weren't writing the same stuff over and over again, but not thinking in terms of how can I be the most abstract possible. So they were trying to provide sort of a minimum layer on top of machine level programming that would let them write code that could run from one machine to another. So in everything they do, they sort of use the most simple representation and don't assume any kind of, there's no array. Most languages would have array bounds checking, and array would be a data structure that would include its size, range of values and stuff. And C just doesn't. So everything about C is sort of the minimum. And it's been around for 40 or something years. So.
But like I believe Pascal kind of precedes that, and there's
No, Pascal does not precede C. No, that's simply not true. Pascal was created as a language for teaching by this fellow named Nicolas Vert. And it was very much an instructional language. So it was really designed to help students who needed help. And C was designed by professional programmers to let them write their code and not get in their way. So they're very different theory between the two languages, right? Yes?
I think the reason that was wrong is because you have like extra brackets at the end of the name.
What's that?
You had extra brackets. After the 16, that was second bracket, there's an extra bracket.
I'm sorry. Oh, yes, that's a mistake there. I'll double check this, or people could check it. I'm pretty sure this code is okay, though. If not, you could certainly say double star b equals a plus 3, and that would work, right? Question? You think what? You think this is 28?
Yeah.
Well, I'm not going to try and hand execute it here, but let's check it. You and I will check this code out, and we'll fix it if it needs to be fixed, okay? Thanks for yeah.
Okay. I feel like he's in the transition period now from what we've already read in the chapter, which is like changes that you can make to programs at the ISA level and above, to just not do things that you don't necessarily need to do, like recomputing values, making unnecessary function calls, and memory references. And now he's transitioning into instruction level parallelism, the microarchitecture, things that you can do to optimize your program for given microarchitecture of the ISA. So this is now below the ISA. And we've been reading a little bit about that, but I want to continue reading more about it. Okay. I just want to take a quick break there and just like relax a little bit, refresh the neurons. Let some of this stuff settle in. All right, so functional unit performance. Figure 512 documents the performance of some of the arithmetic operations for our Intel Core i7 Haswell reference machine. Determined by both measurements and by reference to Intel literature, these timings are typical for other processors as well. Each operation is characterized by its latency, meaning the total time required to perform the operation, the issue time, meaning the minimum number of clock cycles between two independent operations of the same type, and the capacity, indicating the number of functional units capable of performing that operation. We see that the latencies increase in going from integer to floating point operations. We see also that the addition and multiplication operations all have issue times of 1. meaning that on each clock cycle, the processor can start a new one of these operations. This short issue time is achieved through use of pipelining. A pipeline function unit is implemented as a series of stages, each of which performs part of the operation. For example, a typical floating point adder contains 3 stages, and hence the 3-cycle latency. 1 to process the exponent values, 1 to add the fractions, and 1 to round the result. Interesting. The arithmetic operations can proceed through the stages in close succession rather than waiting for one operation to complete before the next begins. This capability can be exploited only if there are successive, logically independent operations to be performed. Functional units with issue times of 1 cycle are said to be fully pipelined. They could start a new operation every clock cycle. Operations with capacity greater than 1 arise due to the capabilities of the multiple functional units, as was described earlier for the reference machine. We see also that the divider used for integer and floating point division, as well as floating point square root, is not pipelined. Its issue time equals its latency. Yep. What this means is that the divider must perform a complete division before it can begin a new one. We also see that the latencies and issue times for division are given as ranges because some combinations of dividend and divisor require more steps than others. The long latency and issue times of division make it a comparatively costly operation. A more common way of expressing issue time is to specify the maximum throughput of the unit. Defined as a reciprocal of the issue time. A fully pipelined functional unit has a maximum throughput of 1 operation per clock cycle, while units with higher issue times have lower maximum throughput. Having multiple functional units can increase throughput even further. For an operation with capacity C and issue time I, the processor can potentially achieve a throughput of C divided by I operations per clock cycle. For example, our reference machine is capable of performing floating point multiplication operations at a rate of 2 per clock cycle. We'll see how this capability can be exploited to increase program performance. Circuit designers can create functional units with wide ranges of performance characteristics. Creating a unit with short latency or with pipelining requires more hardware, especially for more complex functions such as multiplication and floating point operations. Since there is only a limited amount of space for these units on the microprocessor chip, CPU designers must carefully balance these units on the microprocessor. Carefully balance the number of functional units and their individual performance to achieve optimal overall performance. They evaluate many different benchmark programs and dedicate the most resources to the most critical operations. As Figure 512 indicates, integer multiplication and floating point multiplication and addition were considered important operations in the design of Core i7 Haswell processor, even though a significant amount of hardware is required to achieve the low latencies and high degree of pipelining shown. On the other hand, division is relatively infrequently and difficult to implement with either short latencies or full pipelining. Latencies, issue time, and capabilities of these arithmetic operations can affect the performance of our combining functions. We can express these effects in terms of 2 fundamental bounds on the cycles per element values. I'm going to go hit the light here. because I need a little bit more light to read. Okay. So you got a bound, latency, and throughput, and then we got the integer and floating point operations. So integer addition has a latency of 1 and a throughput of 5 because there's 2 functional units, I guess. Floating point has a latency of 3, throughput of 1, because it can be pipelined 3 times. Ten times on the multiplication. Interesting. The latency bound gives a minimum value for the CPE for any function that must perform the combining operation in a strict sequence. The throughput bound gives a minimum bound for the CPE. I should reread this. The latency bound gives a minimum value for the CPE for any function that must perform the combining operation in a strict sequence. The throughput bound gives the minimum bound for the CPE based on the maximum rate at which the functional units can produce results. For example, since there is only one integer multiplier and it has an issue time of 1 clock cycle, the processor cannot possibly sustain a rate of more than 1 multiplication per clock cycle. On the other hand, with our functional units capable of performing integer addition, the processor can potentially sustain a rate of 4 operations per cycle. Unfortunately, they need to read elements from memory creates an additional throughput bound. The 2 load units limit the processor to reading at most 2 data values per clock cycle, yielding a throughput of a bound of half. We will demonstrate the effect of both latency and throughput bounds with different versions of the combining functions. I feel like I want to watch some more of this because he covers some of this and it's not sticking from the reading. I thought the reading would be a little bit more illuminating.
When you do this, the array gets stack allocated as a local array instead of on a heap.
No, that doesn't make any difference at all. In this code? No, where it's allocated makes no difference at all here. So I'll check. That might have to be double star b equals a plus 3. But this was a while ago that I wrote this code. I'll double check it though. Okay, so anyways, that's the sort of end of the story for simple and they are simple optimizations. It's just you have to get in the habit of doing it. Okay, now what we're going to do is go a little bit fancier than this. And as I said, this becomes somewhat more system dependent, but pretty much nowadays all processors have similar implementation. They all do what's known as out-of-order execution, except for the most primitive microcontrollers. And so this is the kind of optimization I'll show. You'll find this general approach will work across quite a variety of machines. So what I'll show you'll find this general approach will work across quite a variety of machines. So what I'm going to do is do this by a series of examples, starting from some not very efficient code and making it run faster and faster. And we'll get a speed up of around 40 just in doing what we're doing. So I'll start by saying, well, assume I have a data structure that looks like the way Pascal implements arrays. Sorry, I have nothing against Pascal. We used to teach it back in the old days. But so a typical way you'd implement an array in a language is you'd provide both the values that are stored in that array And then there'd be other information associated with it. For example, what size it is. And so this is sort of the sort of nice abstract way to do it. And you write code that makes sure that if you ever try to exceed the bounds on the array, you'd return an error signal. And so this particular function you're seeing is when I want to retrieve an element, I pass a pointer, and then that value, the pointer gets used to retrieve the value from the array. And the return value of this function is then just 0 or 1, 0 meaning failure and 1 meaning success. And I'm writing it this way that I use a data type I'll call data_t, and that way I can run this, I can compile this code using different definitions of data_t to get ints, longs, floats, and doubles. And we'll see how the performance characteristics of those shift with the different data types.
I'm curious. Is it godbolt.org? Like Godbolt, not Goldbolt. Can you pass like say I have a struct foo, and we're gonna type def this. Say hey, type def struct foo. Has some fields in here like an int x, int y. We'll call it a point. Point 3D, and you're gonna have int y, int x. We'll make these long z, and then here we'll say point 3D t, like that. Is that a, yeah, it's valid compilation. And we have our main, which will just have an int return, and here we're going to call foo. Well, we're going to declare our point 3D t. We'll just call it x, or that's a bad name. A is equal to 0 initialized. And in here we got to do like dot x is equal to 1, and then dot y is equal to 2, and then dot z is equal to 3. And then here we pass foo a. We'll call this print point a. Or pass the actual a, not a pointer to a. And then we just return 0 here. And then print point a, we'll declare up here. This is a void. Print point takes in a as a point 3D ta. And here we'll say now we need to do a pound include standard io.h, and we go down here and we say, hey, I want to printf out my values here, points, and we'll say %d. Well, we'll do it like this. Say %d, %d, %d. These are going to be the long d's too. And then I'll do a dot x, a dot y, a dot z, and then we put a little new line at the end here. Alright. So now when we look here, is it passing it via pointer? That's what I want to know. So we call here We're using XMM register? No way. Stack pointer stuff. Okay, so we store it on the stack. So we say subtract 72 from RSP, because we get to store 8, 16, 24 on the stack here. 32, 40, 48. This doesn't seem very optimized. And then I say, hey, take 70. Sorry, take 32 RSP offset. Move that into XMM 0. And then we move it back into RSP. So now we have move 3 into 16. What the fuck are you doing, bro? We need some optimization on this bitch. Can I get like an optimization flag? I did OG. Maybe do O1. No, why is this? I guess it eliminated that one needless store. I still don't understand why it's using XMM 0 to store. The fuck is this? Mov DQA instruction. Align double quad word. $16, and we're using 8, 16. We're using more than 16. Okay. So it's just on the stack. We put our return value on the stack as well. And then we also have an 8-byte value here. And then we say, hey, at 16 is going to be our RSI. Yep. What's funny is there's no RSI here. It's just assumed to be passed on the stack. Yeah. Okay, well, that's our answer. It's passed on the stack. Why does it have to do that? Won't printf set EAX? Interesting.
The benchmark I'm going to use is a fairly simple one. It's just for an array or one of these vectors. I just want to combine all the elements of it, either compute their sum or their product. And again, I'm going to use macros here, ident and op.
It's using the LEA to do the addition. It should be 3, 5, 11, right? No, 3, 6, 11. 3, 6, 11 on both of them. Let's try it out. Where are we at here? CSAPP, chapter 05, test, struct args.c. Oh. There you go. Make. CP chapter 03 make file here, as well as .get ignore make file. Okay, lots of shit here we don't need. Delete all that. Delete all that. Looks good. Make. Build. Yeah. So that's the semantics of it. That it gets a copy. So this thing says, hey, copy the value into REX, and then we're just gonna add REX and put it into RCX, RDS. So it copies it from stack into registers. It doesn't do a copy of stack to stack into stack. It knows it needs these values in registers. It's pretty smart. If I did O0, it probably did a full copy, right? Let's see. Where's our stack pointer being used? Used as a base pointer, okay. So we move 16 to REX, we add 2 to it, and then we move REX back into what? That doesn't seem right. Oh no, it's from 16, but this thing got really big because it knows it has 2 values. So it just does the initialization twice. See these mobs, and then oh wait, okay, this is where it does a copy of it, I guess. Yeah, copy the 32 into REX, RDX, 3 into RAX, and RAX into RCX. So it's funny, as I think the optimization build was better. Okay, let's go back to the lectures. Oh no, I killed it. Control Shift T. There we go.
We've now gotten through, but if you trace through what this code will, we used to teach it back in the old. We write code, either compute their sum or their product. Fairly simple. We write code that makes sure that if you ever try to exceed the bounds on the array, you'd return an error signal. And so this particular function you're seeing is when I want to retrieve an element, I pass a pointer, and then that value, the pointer gets used to retrieve the value from the array. And the return value of this function is then just 0 or 1, 0 meaning failure and 1 meaning success. And I'm writing it in this way that I use a data type called data underscore t, and that way I can run this, I can compile this code using different definitions of data underscore t to get ints, longs, floats, and doubles. And we'll see how the performance characteristics of those shift with the different data types. And the benchmark I'm going to use is a fairly simple one. It's just for an array or one of these vectors, I just want to combine all the elements of it, either compute their sum or their product. And again, I'm going to use macros here, ident and op, and define those so that op is addition and the identity value is 0, or the op is multiplication and the identity element is 1, so that I can compare addition and multiplication. So that gives us sort of 8 possibilities here, 2 different operations and 4 different data types. And so this is written in the sort of most straightforward manner, that I'm using this function called getVecElement to retrieve the successive values of this array, and then performing this operation on it. So now to express performance of this, we're going to use a metric I introduced called CPE, which stands for cycles per element. And the idea is that usually when you write code that, say, steps through a vector, anything that has sort of some linear performance as you get bigger, you don't really want to know for exactly, it takes this many seconds or microseconds or nanoseconds to do an operation. You kind of want to know often more what's its overall performance characteristics. And also, it turns out when you're doing low-level code optimization, it's much more useful to think in terms of clock cycles of the inner clock of the processor rather than an absolute term such as nanoseconds. Because whether a processor is running at 2 gigahertz or 2.3 gigahertz, I have no control over that as a programmer, but I can control sort of at the low level how many clock cycles are being used for different parts of the computation. So that's why it's called cycles per element. And you can think of it as, and this shows some actual measurements, that typically a function like this what I showed, the combine, will have some overhead, fixed amount that's associated with setting up the loop, doing the top level call and all that stuff, and then some component that's linear in the size. And so what I want to know is the slope of that linear component. And that will determine, that's what I'll call the cycles per element. You can think of the slope as the sort of incremental cost of adding one more element to the array. So now if I run this function I showed you, and I'm only showing, mostly only show 4 results, because it turns out whether it's int or long or float or double is not going to actually have any effect on performance for most of the cases. So if I just run this code through a compiler and don't do any optimizations, it takes around 20 cycles per element. And if I turn on optimization level 1, which is sort of the first serious optimization, it takes the time in half. So I'm down to 10 clock cycles per element just by changing the compilation. And that's using the most unoptimized code I could think of here. And then I won't go through it all, but using sort of the kind of things I described earlier, of sort of cut away some of the redundancy in this program, you can get it down to something a little bit simpler. And so one thing, instead of, you saw before, I was making a call to this getVecElement, and every time it did that, it went bounds checking. And it's kind of silly to keep bounds checking the same array over and over again when I'm using its length as the determinant of how many elements to access. So if I'm willing to sort of forego bounds checking, what I can do is introduce a function that will just give me the actual data storage part of this vector and skip over all the other stuff. And so I can write a loop and I introduce local variables and all the kind of things we described. And accumulate in temporaries and things like that. Then the program actually gets a lot faster. Again, this is everything from here out is optimization level 1. And so it drops it down to a little over a clock cycle for integers, addition, or 3 clock cycles up to 5 clock cycles for double precision multiply. So that's pretty good. I've sort of definitely improved things. But the question is, well, is that the best there is? And also try to understand what is it about these numbers 3, 5, and this seems to be something close to 1.25. So where are those numbers coming from? And does that indicate some fundamental limitation in my program? Well, in order to do that, you have to have some understanding of the underlying hardware. And there's a really good course you can take. I think it's called ECE 741 that will tell you everything you ever could imagine wanting to know about processor design. And you actually design processors like this. But I'm assuming you're not going to do that for a while because you have about 7 prerequisites to do before that happens. So let me just give you the simple version. And this is sort of an idea of what a processor has looked like since about 1995. So this is old stuff, but it's enough actually to really understand it. It's so hard. It's really, the details are pretty massive. And so it's not even taught, for example, 447 is the ECE is the computer architecture course, and they don't really go into this kind of design here because they're pretty hard. They're actually hard to design on your own. But the basic idea is you think about a program as the computer just reads in an instruction, does whatever it says to do, reads in another instruction, does what that says to do. And that has nothing to do with how programs actually execute. What they've built up is this massive hardware infrastructure to make a program run way faster than it would if it were just doing one instruction at a time. And it employs a technique that's called superscalar out-of-order execution. And the idea is, roughly speaking, it takes your program, if you think of your program as a linear sequence of instructions, and it just sucks in as many of those as it can, and it pulls it apart to realize that certain operations don't really depend on each other. So I can start one even though it's later in the program than the one I'm working on right now because they're independent of each other. And it's extracting what they call instruction level parallelism, places where even though your program is a linear sequence of instruction, buried in there is actually a sort of forest of different computations that need to be done, some of which depend on each other and some of which don't.
That's right. I remember that from the previous parallel computing course that I audited. Data level parallelism.
A bunch of hardware. And so that's up here. This upper part shows this idea of fetching instructions. So there's a cache memory, a high-speed local memory that is just pulling in your instructions as fast as it can. And those instructions are then feeding a big pile of hardware that will extract out of it these low-level operations and figure out which ones depend on which others. And then there's a set of functional units in this part of it that are able to perform these low-level operations, to do arithmetic, floating point operations, to read data from memory, to store data back to memory, all using a cache, which is something you're going to learn about fairly soon, what all this cache is. But think of this as a high-speed copy of some of the data memory. And so what this logic tries to do is keep forking out, spawning off operations based on your program, and keeping these as busy as they can be, doing different fragments of your code, doing different instructions in a different order from before. And it turns out, you think of a register as the set of registers is a part of memory that get read and written. It turns out that in executing, a register now just becomes the name of something that one instruction produces and some other instructions consume. It's a destination for some, it's a source for others. And this whole bunch of stuff here just sort of magically passes the results of one computation to the input to another computation based on register names without ever storing them in an explicit register file. There is a register file. When things kind of settle down, they get stored away. Anyways, there's a lot of stuff going on here. But the main thing to think about is your machine has resources to do multiple operations all at the same time if you can somehow structure your program so that those can all get used. So this is, as I mentioned, it's called a superscalar processor. It's one that can do more than one instruction every clock cycle. And actually, Intel started in '93. The very first Pentium could do 2 instructions at once. But then a little later, they came out with one called the Pentium Pro, which is sort of the basis of all modern processors. And the lead architect, by the way, was a CMU graduate. This out-of-order execution is the model that's used nowadays. So the other thing is those functional units are more complex than you think they might be, in that they have what's called pipelining. And the idea of pipelining is, imagine you can break up a computation into a series of distinct stages. A simple example is if you want to compute a times b plus c, you first do the times and then you do the plus. But it actually gets deeper than that. You can take something like multiplication and break it up into smaller steps that can be done one after the other. In a way that, and then if you have a separate dedicated hardware for each of those stages, then you can do what's called pipelining, which is when one operation moves from one stage to the next, a new operation can come in behind and start its thing. So this example shows, imagine I had a 3-stage pipeline multiplier, and I want to do this computation, a times b, a times c, and now multiply those together. So the thing to observe is that a times b and a times c don't depend on each other in any way. So I can do them both. And I don't have hardware to do them simultaneously, but I have them enough to do one right after the other. So I can feed the first computation into the first stage, a times b, on time step 1. And then time step 2, it will move on to stage 2. And time step 3, it will move on to stage 3. But now I can start a times c in the time step 2, because this stage became available once a times b moved from stage 1 to stage 2. And so I can follow right behind, just one clock cycle behind this other operation. Now, p times 1 times p2 obviously depends on both of these products. So it can't start until a times c is completed, and then it will run through the pipeline without anything else. So overall, then, we've done what would have normally seemed to be 9 steps worth of arithmetic in a total of 7 steps here because of pipelining. Question?
If there is more than one core, would it be possible to do 2 stages at the same time?
If you had, like in this picture here, if there were different multipliers in these different places, yes, you could do those 2 completely independent of each other.
So it's like a core, like would all those like multipliers and everything, is that like what would be in a core?
Yes, this is all in a single core of a single processor. Multi-core is yet another. This is a lower level parallelism than you get through multi-core. And it's present except in the sort of lowest end, lowest powered embedded processors. Some version of this exists. And most of the time, your hardware is not being fully utilized. Is one thing you're going to learn from this. So that's the idea of pipelining. It's sort of like parallelism, but it's not that you have multiple copies of resources. It's that you have this ability to stream operations through a single hardware resource in close succession to each other. And so Haswell, which is a little bit more recent than the Shark machines, but not that much more, is one of the most recent versions of the Intel x86 series. And the functional units include, there's a lot of functional units that can do different things, but when you add it all up, there's a possibility of it doing 2 loads in 1 store, 4 integer operations, 2 floating point multiplies, 1 addition, and 1 division. They can't all happen at the same time because there's some are shared functional units. But the point is there's really a lot of equipment there that can do stuff. And also, you can measure how an instruction now has two characteristics. An operation is how long does it take from beginning to end, but also how closely spaced can two operations be because of this pipelining. So you see that most of them take some number of clock cycles to perform, but they're also pipelines so that you can do a series of them just one cycle apart. The only different ones that aren't is you'll notice the division is both very slow and it's not pipelined. And division is a very expensive operation on most machines, relatively speaking. So what I claim then is these characteristics then provide a limit on how fast our program can run, our original program. In that I have a series of multiplications, for example, of integers here. And this shows the code for it. And the result of, I need the result of one multiplication before I can begin the next. So there's a 3 clock cycle bound here. And you'll see that, in fact, my measurements all correspond to what I'm calling the latency bound of these machines, which is just based on how much time it takes from a beginning of an operation to the end. And the reason is we can sort of diagram the computation being done by this program, that it's doing a series of multiplications, and I require the result of one multiplication before I can start the next. In general, if you look at this loop code, it has to compute ECX, the updated value of it, before it can now start the next one. And so that's why, even though I have a pipeline multiplier, my program itself limits me to the sequential execution of all the multiplies. So let's see if we can't get beyond that bound, that latency bound. Well, there's a fairly common technique that you might have heard of before that's called loop unrolling. And the idea of loop unrolling is just that you
we are not at loop unrolling yet in the book, so I'm not going to continue on yet. Let's review from where we left off here. Latency bound gives a minimum value for the clocks per element for any function that must perform a combining operation in a strict sequence. The throughput bound gives a minimum bound for the CPE based on the maximum rate at which the functional units can produce results. For example, since there are only one integer multiplier and it has an issue time of 1 clock cycle, the processor cannot possibly sustain a rate of more than 1 multiplication per clock cycle. On the other hand, with 4 functional units capable of performing integer addition, the processor can potentially sustain a rate of 4 operations per cycle. Unfortunately, the need to read elements from memory creates an additional throughput bound. The 2 load units limit the processor to reading at most 2 data values per clock cycle, yielding a throughput bound of 0.5. We will demonstrate the effect of both latency and throughput bounds with different versions of combining functions, an abstract model of processor operation. As a tool for analyzing the performance of machine-level programs executing on a modern processor, we will use a data flow representation of programs, a graphical notation showing how the data dependencies between the different operations constrain the order in which they are executed. These constraints then lead to critical paths in the graph, putting a lower bound on the number of clock cycles required to execute a set of machine instructions. Before proceeding with the technical details, it is instructive to examine the CPE measurements obtained for function combine 4, our fastest code up to this point. So our latency bound is 1, our throughput bound is half. 3 and 1, 3 and 1, 5. we can see that these measurements match the latency bounds for the processor except for the case of integer addition. This is not a coincidence. It indicates that the performance of these functions is dictated by the latency of the sum or product computation being performed. Computing the product or sum of n elements requires around L times n plus k clock cycles. Where L is the latency of the combining the operation, k represents the overhead of calling the function and initializing and terminating the loop. The CPE is therefore equal to the latency bound L. Yeah, makes sense. From machine level code to data flow graphs, our data flow representation of programs is informal. We use it in a way to visualize how the data dependencies in a program dictate its performance. We present data flow notation by working with combine for. As an example, we focus on just the computation performed by the loop, since this is the dominating factor in performance for large vectors. We consider the case of data type double with multiplication as its combining operation. Other combinations of data type and operation yield similar code. A compiled code for this loop consists of 4 instructions with the registers RDX holding a pointer in the ith element of array data, REX holding a pointer at the element of the array, and XMM holding an accumulated value ACC. Okay. Let's look at the code here. So we multiply accumulated by data I, we increment data I, data plus I by 8, compare to data plus length to see if we're at the end. If not, we go to loop. So we're using XMM, RDX, RAX in the whole thing. Looking at the diagram. Graphical representation of inner loop code for combined for instructions are dynamically translated into one or two operations, each of which receives values from the operations or the registers and produces values for the other operations and for registers. We show the target of the final instruction as the label loop. It jumps to the first instruction shown. So you got load and multiply, add, compare, and jump. Jump has a dependency on comparison. Multiply has dependency on load. But the load, we're reading from RDX and memory. And we're writing that into XMM. XMM is then used for multiply. Or read from XMM, sorry. Because XMM is our accumulator. So XMM goes into multiply. So we multiply data load and XMM and we write it to XMM. Then we add RDX. 8 to RDX. And write it back out to RDX. And also use it for the comparison. The RAX. As figure 513 indicates, with our hypothetical processor design, the 4 instructions are explained by the instruction decoder into a series of 5 operations, with the initial multiplication instruction being expanded into load operation to read the source operand from memory and a mul operation to perform the multiplication. As a step towards generating a data flow graph representation of the program, the boxes and lines along the left-hand side of figure 513 show how registers are used and updated by the different operations, with the boxes along the top representing the register values at the beginning of the loop, and those along the bottom representing the values at the end. For example, register REX is only used as a source value by the compare operation, so the register has the same value at the end of the loop as at the beginning. Register RDX, on the other hand, is both used and updated within the loop. It's getting hot in here. So initial value is used by the load and add operations. This new value is generated by the add operation, which is then used by the compare operation. Register XM0 is also updated within the loop by the multiply operation, which first uses the initial value as source values. Some of the operations in figure 513 produce values that do not correspond to registers. We show these as arcs between operations on the right-hand side, and the load operation reads value from the memory past it directly to the mul operation. Since these two operations arise from decoding a single mul SD instruction, there is no register associated with the intermediate value passing between them. The compare operation updates the conditional codes, and these are then tested by the J&E operation. For code segment forming a loop, we can classify the registers that are accessed into 4 categories. We arrange the operators to more clearly show data dependencies, and then further show only those operations that use values from one iteration to produce values for the next. So if read-only, these are used as source values, either as data or to compute memory addresses, but they are not modified within a loop. The only read-only register for the loop is combined 4 is REX. Okay. Write only, these are used as destinations for data movement operations. There are no such registers in this loop. Local, these are updated and used within the loop, but there is no dependency from one iteration to the next. The condition code registers are examples for this loop. They are updated by the compare operation and used by the jump not equal operation, but this dependency is contained within individual iterations. Loop, these are used both as source values and as destination for the loop, with the value generated in one iteration being used in another. We can see that RDX and XMM0 are loop registers for combined 4 corresponding to program values data plus I and accumulator. As we will see, the chains of operations between loop registers determine the performance limiting data dependencies. Figure 514 shows further refinement of the graphical representation of figure 513 with the goal of showing only those operations and data dependencies that affected program execution time. We see in figure 514A that we rearrange the operators to show more clearly the flow of data from source registers at the top, both read and only and loop registers, and the destination registers at the bottom, both write only and loop registers. In figure 514A, we also color operators white if they are not part of the chain of dependencies between loop registers. For example, the comparison compare branch J&E operations do not directly affect the flow of data in the program. We assume that the instructions control units predict the branch will be taken, and hence the program will continue looping. The purpose of to compare the branch operation is to test the branch condition and notify the ICU if it is not taken. We assume this checking can be done quickly enough that it does not slow down the processor. Okay, almost done with the reading here. We'll finish the reading, then we'll come back to the problems this evening. and then we'll pick up on loop unrolling tomorrow. Figure 514b, we have eliminated the operators that were colored white on the left, and we have retained only the loop registers. What we have left is an abstract template showing the data dependencies that form among loop registers due to one iteration of the loop. You can see in the diagram that there are two data dependencies from one iteration to the next. Along one side, we see the dependency between successive values of program value accumulator stored in register XMM0. The loop computes a new value for the accumulator by multiplying old value by a data element generated by a load operation. On the other side, we see the dependencies between successive values of the pointer, the ith data element. On each iteration, the old value is used as the address to a load operation, and it is also incremented by the add operation. It's new value. Yeah, okay. Figure 515 shows the data flow representation of n iterations by inner loop, a function combine for. This graph was obtained simply by replicating the template shown in figure 514b n times. You see that the program has two chains of data dependencies corresponding to updating program values of accumulator and data plus I with operations mul and add respectively. Given that floating point multiplication has a latency of 5 cycles, while integer addition has a latency of 1 cycle, we can see that the chain on the left will form a critical path requiring 5 n cycles to execute. Chain on the right, would require only n cycles to execute, and so it does not limit the program performance. Figure 515 demonstrates why we achieved a CPE equal to a latency bound of 5 cycles for combine 4. When performing floating point multiplication, when the execution of the function, the floating point multiplier becomes the limiting resource. The other operations required during the loop, manipulating and testing the pointer value, data plus I, and reading data from memory, proceed in parallel with the multiplication. As each successive value of accumulator is computed, it's fed back around to compute the next value, but this will not occur until 5 cycles later. The flow or other combinations of data type and operations are identical to those shown in figure 515, but with different data operation forming a chain of data dependencies. Shown on the left, for all these cases where the operation has a latency L greater than 1, we see that the measured CPE is simply L, indicating that its chain forms the performance limiting critical path. Other performance factors. For the case of integer addition, on the other hand, our measurement of combine 4 shows CPE of 1.27, slower than CPE of 1. We predict based on chains of dependencies formed along either the left or right hand side of the graph, figure 515. This illustrates the principle that the critical paths in the data flow representation provide only a lower bound on how many cycles a program will require. Other factors can also limit performance, including the total number of functional units available and the number of data values that can be passed along the functional units at any given step. For the case of an integer addition as the combination operation, the data operation is sufficiently fast that the rest of the operations cannot supply data fast enough. Determining exactly why the program requires 1.2 cycles per element would require much more detailed knowledge of the hardware design than is publicly available. To summarize, our performance analysis of combine 4, our abstract data flow representation of the program operation showed that combine 4 has a critical path of length L times n caused by successive updating of the program value accumulator, and this path limits the CPE to at least L. This is indeed the CPE we measure for all cases except integer addition, which has measured CPE of 1.27 rather than a CPE of 1. We would expect from the critical path length, it may seem that the latency bound forms a fundamental limit on how fast our combining operations can be performed. Our next task will be to restructure the operations to enhance instruction level parallelism. We want to transform the program in such a way that our only limitation becomes the throughput bound, yielding CPEs below or close to 1. Okay. We got 9 minutes. Let's see what these problems look like. I might just skip them, because I want to get through this chapter. Suppose you wish to write a function to evaluate a polynomial where a polynomial's degree n is defined to have a set of coefficients. For a value x, we evaluate the polynomial by computing so and so. This evaluation can be implemented by following the following function. having an arguments an array of coefficients a value x, and a polynomial degree, the value n in the equation. In this function, we compute both the successive terms of the equation and the successive powers of x within a single loop. For degree n, how many additions and how many multiplications does this code perform? For our reference machine with arithmetic operations having latencies shown in figure so-and-so, we measure CPU of this function to be 5, explain how the CPU rises. I don't care about this. I don't want to evaluate polynomials, I'm sorry. Alright, we're at loop unrolling. I'm going to take an early break here for dinner. And I will be back. I also have to do laundry. I'll be back, let's see, I'll be back at 6 p.m. And I don't know if I'm going to pick up with loop unrolling here or not. So we have loop unrolling, enhancing parallelism. I want to just get a feel for how much. And then summary of results for optimizing code. Some limiting factors. I forget how many sections are here. Understanding memory performance. That's a whole section there. Life in the real world performance improvement techniques. High-level design, basic coding principles, low-level optimizations, identifying and eliminating performance bottlenecks. Finally, summary. So that's 604. We're at 567. So we got another 17 pages read. Yeah. Okay. I think I might do some reading, or I might pick up the Learning Linux Binary Analysis book tonight just to change up some things, because I don't want to get too burned out on this stuff. All right, I'm going to take a break here then. I will be back on at 6 p.m.